Hi, in this video we are going to be looking at circle theorems, and in particular we're going to be looking at the relationship between the central angle and the angle on the circumference, or what we call a inscribed angle. Now if we look at this circle with center at O, the angle AOB, which we're going to designate as alpha, is a central angle and is subtending to the arc AB. Now, the angle ACB, which we're going to designate by beta, this angle is subtending the same arc. Subtending means its arms go through the same points A and B. And what we want to prove is that this angle beta is always equal to half of alpha. So beta is equal to alpha over 2. And it doesn't matter where the point C is on the circumference. If here I'm showing the C has moved a bit, this angle C, ACB, is the same as this angle AOB. Even if it moves further here, this angle ACB, it is still equal to half the angle AOB. I'm sorry if in the previous slide I said it's equal to AOB, it's incorrect. The angle on the circumference is always equal to half the angle at the center subtended to the same arc. So now we're going to set out to prove this. Before we do that, we notice that if even C is on this arc, this means C is now subtending the longer arc AB and is equal to half the value of this angle AOB, which is larger than 180 degrees. So wherever C is, the angle ACB is equal to half the angle AOB, where O is the center. And as we just saw, if I move C into the shorter arc, this angle is half the AOB, the reflex angle AOB, which is greater than 180 degrees. And now we're going to set out to prove that. Okay, supposing we have this diagram, we have a circle and AB is an arc of the circle. We want to show that the angle AOB is half the size of the, AOB is twice the size of ACB. Now, if I designate this point, let's call this point E for convenience. Now, in this triangle OBC, OB and OC are the radii of the circle, so they are equal. Therefore, the triangle OBC is an isosceles one, because OB is equal to OC, which means this angle, if I call this little alpha, is equal to this angle. Now, the angle here, which I will designate as beta, is an exterior angle to the triangle OBC, and we know that exterior angle here, beta, is equal to the sum of the other two angles. So beta is equal to alpha plus alpha, which is equal to 2 alpha. With a similar argument, we can show that triangle AOC is an isosceles one because these two lengths, AO and OC, are equal in length. Therefore, AOC is an isosceles triangle, and this angle here, let's call this gamma, is equal to that angle. Now, this angle here, phi, sorry, using all these Greek letters, this is an exterior angle in the triangle AOC and is equal to sum of the other two angles. So phi here will be equal to 2 gamma. Okay, now if we look at the angle AOB, we can see that it is equal to phi plus beta. Now if I look at the angle ACB, the angle sign on top of it, this is equal to, let's put the equal sign here as well, gamma plus alpha. Now, we can see from our relationship here to the right that beta is equal to 2 alpha and phi is equal to 2 gamma. So phi plus beta will be equal to 2 alpha plus 2 gamma. Therefore, if we look at these two relationships, AOB is equal to 2 times alpha plus gamma, and ACB, these are angles we're talking about, is equal to just alpha plus gamma. Comparing the two, we will see that the angle AOB is equal to twice the angle of ACB, which completes our proof. That means the angle on the circumference is equal to half the central angle subtending to the same arc. Now, this was a point where the position C is such that the two lines AB and AC are on different sides of the angle AOB. If they are not, we can still prove this theorem, which is what I'm going to do now in the next slide. Okay, now in this situation, the point C is such that AC cuts through our angle AOB, i.e. the two arms of the angle ACB are not either side of the angle AOB, which looks a bit complicated, but we can use the same reasoning. By the same reasoning that we used in the previous proof, in triangle OBC, OB and OC are radii of the circle, so OBC is an isosceles triangle. Therefore, these two angles in black are alpha, i.e. the angle OCB and OBC. By the same reasoning, in triangle AOC, OC and OA are radii of the circle and they're equal in length. Therefore, AOC is an isosceles triangle, and these two angles will be the same, which are marked in red, which are beta. Now, in triangle OBC, the angle EOB is an external angle. So the angle EOB will be equal to the sum of the other two angles, which is 2 alpha. In triangle OAC, the angle EOA becomes an exterior angle, and it's equal to the sum of the other two, which are the two red angles here. So we can write the angle EOA. This will be equal to 2 beta. Now our central angle AOB, that's the angle that we're interested in, is therefore equal to the difference between the angle EOB and EOA, which will be 2 alpha minus 2 beta. I have just noticed, I'm not sure if anybody else has, that this shouldn't be EB, this is EOB up here. I could have edited this out, but I didn't, because it helps you see that we all can make mistakes, so we should be very careful when we are writing equations, etc. Anyway, the angle AOB, which is our center angle, is equal to 2 alpha minus 2 beta. Now, the angle ECB, I'll write this here, ECB, will be equal to the difference of these two angles, the black one and the red one, which will be alpha minus beta. By the same reasoning, when we compare these two, we will see that this angle is half of angle AOB, and therefore here we again prove that the angle AOB is equal to twice the size of the angle ECB. You may be required to know these proofs in an exam, but I hope I have clarified how you can prove this. Please give this video a like and click the subscribe button so that you will get alerts of all my future videos. Thank you very much for watching.